Okay, let's look at Chapter 7, Section 2, looking at rational exponents. So kind of let me extend this notion to you really fast. Let me bring this up. So it's common, we already know that if n is a natural number, remember the natural numbers are the counting numbers. They're the set of numbers 1, 2, 3, 4, and they just go on forever. So they're basically positive whole numbers. So if n is a counting number and b is any real number, b to the n is equal to b times b. So that's pretty natural. At some point we added to the set the element 0, and this is the whole numbers, so it never hurts to review. This is the set of natural numbers. When I add 0 to the set, I get the set of whole numbers. So we already know what b to the n means when n is in this set, the natural numbers. So all I have to do now is extend the meaning of b to the 0. And we learned that b to the 0 is equal to 1 provided b is not equal to 0. And then at another point we said, okay, let's extend our exponents even more from the whole numbers to the integers. So these are the integers. So it's positive and negative natural numbers plus 0. And we learned that, for example, b, if n is a natural number, then minus n is negative, is equal to 1 over b to the n. And finally, way back, maybe not in a class that you've had, we extended the set of numbers to include fractions, a over b, such that a and b are integers. B is clearly not equal to 0. This set of numbers is called the rational numbers. And what we're going to do now is extend the meaning of a base b raised to a rational exponent. So that's just something mathematicians do in general, and that's the context for 7.2. We're just pushing the boundary, so to speak. So let n and m be positive numbers greater than 1. Then 1a to the 1 divided by n, I'm right here in the reading, is equal to the nth root of a. And a to the m divided by n, so this is a fractional exponent, is equal to the nth root of a to the m. So I'm going to make one little clarification here for this very last part right here. Really, you have two options for this. So a to the m divided by n can be expressed as one of two things. The nth root of a raised to the mth power, but that's exactly the same as the nth root of a, the whole thing, raised to the mth power. I just reviewed your book, And your book gives the following. I use this myself. The book says this form is more useful. But for some of you who have a memory and recall, we defined it this way in a previous lecture. So, go on down. And we also have what is completely natural, a to the minus m over n is equal to 1 over a to the m over n. So we do just like we do before with negative exponents. So b to the minus n is equal to 1 to b to the n. So if I want to make that a fraction, I can. In other words, the rule was if I have a negative exponent, I can make it positive by moving the entire term across the division line. The price you pay is the sign of the exponent changes. And of course, when you move it, it's not replaced with 0, it's replaced with 1. The same exact thing is going here. So we also have the rule 1 over a to the minus m divided by n is equal to a to the m over n. So we can move, if we have a negative exponent, we can move it across the division line. And of course we can go even further. This is equal to the nth root of a to the m power, because that's what a to the m divided by n power means. So let's do some problems. So again, this is really an awful lot. I just created your homework today for it. I don't know what happened. I lost the homework I created for another class. So I recreated yours, and I kept it really simple. In almost every case, there's fewer than 10 actual problems, although there might actually be in number more problems with that. The first few are vocabulary problems, and they're really simple and easy. And your exam, both in my math lab and the Canvas portion, is also going to stick with really, really simple details, although we will actually go into more in-depth details in the lecture. But for your exam, for both the MML portion and the Canvas portion, we're going to keep it simple. So we are instructed to do what? We want to use radical notation to write the following. Simplify if possible. Simplification is kind of a tricky thing. A simplification in one context may not be a simplification in another, but I'm going to show you what they're aiming for. So this is example. Where's my pen? Oh no, I've lost my pen. Hold on just a second. I'm going to unplug my bamboo tablet and plug it back in. It usually does it. Yeah, we got it back. So this is going to be 1a. I'll make my pen just one hit bigger. So we have 4 to the 1/2 power. Well, that's equal to the second root of 4 to the 1. But remember, when the index is 2, that's just the same as the square root, and 4 to the first power is just 4, so the square root of 4 is equal to 2. So that's not so bad. So we're going to do 1b. So we want to do 64 raised to the 1/3 power. So by definition, that's the third root of 64 raised to the first power. We don't have to put the first power there because it's just by definition that a to the 1 over n is equal to the nth root of a. But I can simplify this. And what I need to do to simplify this is I need to transform 64 to something raised to the third power. But if we recall, 4 raised to the third power is equal to 64. So our index is odd, and by a rule that we learned in section 7.2, I have index, the nth root of a to the n is equal to a when n is odd. So since n, my index is odd, my answer is 4. So let's do example 1c. So we want to do 5 times y to the 1/3 power. Well, you might want to isolate it this way. You don't have to. Y to the 1/3. But that's equal to 5 times the third root of y. And that's all we can do. There can be no further simplification of that. And let's do 1d. We want to do, now notice my base here is 81 x to the 8th power. Over here, my base for the fractional power 1/3 is just y. 5 multiplies by whatever this number is, and that's the reason I rewrote it this way. But here, if we look there, my base is 81 times x to the 8th, and that's raised to the 4th power, to the 1/4 power. So that's the 4th root of 81 times x to the 8th. So I want to write 81 as something to the 4th power. X to the 8th will not be difficult. So 8 divided by 4 is equal to 2. So x to the 8th is x squared to the 4th, because 2 times 4 gives me 8. So that takes care of one of the problems. That's x squared to the 4th power. But what is 81 to the 4th power? Well, if we think, we know 81 is 9 squared, but 9 itself is 3 squared. So 3 squared squared is 3 to the 4th. So 81 is 3 to the 4th. So I can finally use another exponent rule. So your exponent rules are really important. This is the same as 3 times x squared as my base raised to the 4th power. Now notice my index is even. And we learned if n is even, then the nth root of x to the n is equal to the absolute value of x. Will we need to use the absolute value this time? Well, we're going to find that we don't need it. So the question is, I know that the answer is 3x squared. Do I need to put an absolute value around the x squared? And I don't, because x squared is always greater than or equal to 0. So the absolute value of x squared is always just equal to x squared, because the absolute value of a number that is always greater than or equal to 0 is just that number. So we can ax the absolute value, and it's just 3, not x, 3x x squared. Okay, so let's do some more examples. Lots of examples. So for example 2, we want to use radical notation to write the following, and we want to simplify whenever possible. So this is example 2a. So I have 16 to the 3 halves. So let's give ourselves some more room. That'll do for right now. 16 to the 3 halves. So by definition, the denominator becomes my index, and 16 is my base to the raised to the power of the numerator. But remember, when my index is 2, that's the same thing as the square root of 16 cubed. I'm going to keep the index in there. Sometimes it's helpful, because in order to find that out, find out the answer here, I want to somehow express 16 cubed as some type of a square. So 16 is equal to 4 squared. So 16 cubed is 4 squared cubed. But that's equal to the second root of 4 cubed squared, because 2 times 3 is the same as 3 times 2. So now the answer is 4 cubed, which is equal to 4 times 4 times 4, which is 64. Again, using this rule, the nth root of some number raised to the nth is equal to that number. In this case, that number here was 4 cubed. So now let's do number B. 2b. Let me check something really fast. Okay. I have a nightmare of doing these lectures because it's already happened once. And an hour and a half later, I go to stop the recording and I never turned it on. So that's an hour and a half I have to redo. So we have -1 to 3/5. Well, by definition, this is the 5th root of -1 raised to the 3rd. Well, can we in any way simplify this? Well, -1 times -1 times -1 is -1 raised to the 3rd. So this is the 5th root of just -1. But -1 times -1 times -1 times -1 times -1, what I just did there was I multiplied -1 by itself 5 times, and I got -1. So the answer turns out to be -1. Now we'll do 2c. And I just looked, and I apologize, I usually stick to the exact problems by example number is given in your textbook. But for some odd reason, this time I did not. And I'm using problems taken from the same area, but they're not identical. So this is the denominator becomes my index, and the 3x plus 2 is my base raised to the power of the numerator. And the only simplification I can do is just an aesthetic one. We certainly do not want to do too much with here, but we can do this. We can write 3x plus 2 squared times 3x plus 1. So the answer is 3x plus 2 squared times 3x plus 1. And you're saying, what? And you should be. For right now, just leave it like that and say it's fully simplified. But I want to show you what I did. Suppose I want to take the second root of b, not to the fifth, but b to the third. Well, that's equal to the second root of b squared times b, which turns out, a property we've not yet learned, turns out to be the square root of b squared times the square root of b. So the square root of b squared is b times the square root of b. So for right now, just ignore everything, and in your mind, you can absolutely stop right here and say finished. And I'm pretty sure that's exactly what the example does in the corresponding text. So now we're going to do example 2D. So this is minus, this is my base, 81, and my base is raised to the 3/4 power. So this is equal to minus my denominator comes my index, and my base 81 is raised to the 3rd power. Well, again, I want this raised to a 4th power, so I recall what I did earlier, and that 81 is 3 to the 4th power. So 81, I'm using the fact that 81 is 3 to the 4th. So 81 to the 3rd power is 3 to the 4th to the 3rd power. So you've got to get used to this trick right here. Our law of exponents says a to the m a to the nth power itself raised to the mth power is equal to a times n times m. But that's equal to a times m times n, because this is multiplication, and the order of factors in multiplication doesn't matter. So by the same token, this is a to the mth raised to the nth power. So that's what I'm going to do right here. I'm going to exchange these two numbers. And that's what I want. So the answer is my minus is still there, and the 4th root of 3 to the 4th is a positive number, right? But 3 cubed is already positive, so I don't need any absolute values. If you wanted to, you could put them there, but they're not needed at all, because 3 to the 3rd is 27, and 27 is already positive. So that's minus 27. And let's do number E. Okay. I have 1 25th, that's my base, raised to the 3/2. Well, that's the square root. And if you want to put the 2 there, that's fine. Just remember, when the index is 2, it's the same as the square root of 1/25th raised to the 3rd power. But that's equal, by our exponent rules, to the square root of 1 cubed over 25 cubed. But 1 cubed is just 1. 1 times 1 times 1. And 25 is 5 squared. So 25 cubed is 5 squared cubed. So coming back over here, so that's equal to the square root of 1. And I'm going to play that little trick, and I'm going to exchange the positions here of my exponents. 5 cubed squared, which is equal to the square root. A lot of manipulations here, but they're pretty trivial. Over 1 over 5 cubed. The whole thing is squared. That's another exponent rule. So now the answer is 1 over 5 cubed, which is equal to 1 over 5 times 5 is 25, times 5 is 125. Okay, we got through the first page. The next page is just right down here. I just want to show you all of our rules for exponents now actually hold just exactly the same when our values of m and n are rational numbers. Everything holds exactly the same. So the product rule for exponents, let m and n be rational numbers. Rational numbers, rational numbers. But let's go up here and do number 3. So now we're just going to do some negative exponents. You can kind of see the drill. So you might want to try to do number 3a by yourself. We're going to simplify 16 to the minus 3/4. So I want to make this a positive exponent. So I'm going to move the 16 raised to the minus exponent under the division line. And the price to be paid is that the exponent changes sign. And of course, when you move it, it's replaced by a 1, not a 0. So now literally all I have to do, all of the work that I do, is now in the denominator. And if you look back just another page, or just what we did, we learned that 16 is 2. Well, maybe we didn't, but 16 is 2 to the 4th, because this is a 4th root. I think we were doing square roots earlier. So again, I'm going to use that same trick. 1, the 4th root of 2 cubed raised to the 4th power. So now I can use my simplification, because that's the 4th root of some number raised to the 4th. So the answer is just that number, 2 to the 3rd, and that's equal to 1. 2 times 2 times 2 is 8. (3b). So my base is negative. Negative 27 raised to the minus 2/3. So the first thing I'm going to do is I'm going to make that exponent positive. By moving it under the division line. And now I'm going to convert it into radical notation. That's the third root, and my base is minus 27, and that is squared. So the base is minus 27, so you need to put it in parentheses. Well, that's equal to 1 over the cube root of 27 is minus 3 minus 27, sorry, is minus 3 cubed. And that is raised to the second power. So I'm going to still do my little switchy thing. And this is going to be minus 3, it's my base, raised to the second power, raised to the third power. So now I can immediately detect or see what the cube root is. And the cube root is 1 over what's raised to the third power, which is minus 3 squared, which can be further simplified to 1 over minus 3 times minus 3 is 9. So that's equal to 1/9. Okay. So I've already went over rules for exponents. Again, the only thing that has to be mentioned here are these are the exact rules that you're seeing before, but before those rules had let m and n be integers. Now they can literally be rational numbers. Some of these look nasty, but we'll just go at them step by step using exponent rules. So here, this is number 4, 4a. I have some base b raised to the 1/3 power times some base b raised to the 5/3 power. So we have a rule for exponents that says a to the mth power times a to the nth power, as long as my bases are the same. That's a raised to the m plus n. So my bases here are the same. So this is b raised to the 1/3 plus 5/3 power. Well, that's just simply b excuse me, raised to the 6/3 power. But I can, just like any fraction, just because the fraction's in the exponent doesn't mean I can't simplify it. And 6 divided by 3 is 2. So this is actually equal to b squared. Not near as bad as it looked, right? So 4b, x to the 1/2 power times x to the 1/3 power. That's equal to x. The bases are the same, so I can add their powers. And the LCD of 2 and 3, they don't share any common factors, so it's the product. So this is x raised to the 3/6 plus 2/6, which is x raised to the 5/6 power. And they want you to write it with positive exponents. So you just kind of have to read the instructions. and it says write results with only positive exponents. So if you're tempted to go ahead and say, oh, well, that's the 6th root of x to the 5th, this is indeed correct, but they want it written in exponent form, so we simply stop right here. So I know my math lab is aggravating for a lot of you, but go slow, read the questions very, very carefully, and if it's on an exam, no matter when, even when you take the My Math Lab exam at some different time, you can always risk emailing me for help as to how to enter in your answer. It's a risk because I have my email up all night long. It's in the very room you don't see, but there's another desktop computer behind you, and in my bedroom I have another computer, and I'm doing this on a laptop. Of course, it's like you can't see the laptop, but my laptop has better processing speed, so I'm using that one. So I have computers everywhere, and the email is almost always up, and it makes a little sound, and if I hear it's an email, I will actually address it. So we're doing 4C. If you, that's all I'm going to say about that. 7 to the 1/3 divided by 7 to the 4/3. So what I'm going to do is I'm going to move, since 1/3 is less than 4/3, I'm going to move this term. I'm going to keep 7 to the 4/3 underneath the division line, and I'm going to move this term underneath, and the operation there is multiplication, and it's replaced by a 1. So now all I have to do is simplify what's in the denominator. Well, our bases are the same, it's 7, so I simply add my denominators. So the answer is 1 over 7 raised to the 5/3 power. And that's how they want to see it. Oh, wait. Sorry. I forgot to do something. This big, huge spiel about the price you have to pay when you move a term under the denominator. You get to talking, you forget to pay the price. The price is that it becomes negative. My exponent has to be negative. Now let's proceed. That's 1 over 7 to the 4/3 minus 1/3, which is equal to 1 over 7 to the 4 minus 1 is 3 divided by 3. So that's equal to 1 over 7. 3 divided by 3 is 1. So that's just equal to 1/7. And finally, let's do number D. It looks more hideous than it really is. But it does involve adding some fractions and subtracting some fractions. So let's just tackle it. This is 4D. So I have as my base 2x to the 2/5 power times y to the minus 1/3. All of that is raised to the 5th power over x squared y. So thinking about PEMDAS, there's really nothing I can do to simplify what's in parentheses. I could move the y to the 1/3 under the division line, which would result in the numerator itself being a fraction. That's not a simplification. Let's use this rule. It's the power of a product rule. A times b raised to the nth power is a to the nth times b to the nth. So this is 2. This is factor 1, factor 2, factor 3. This is a product of 3 things. So this is my first factor raised to the 5th power. My second factor, which is x to the 2/5, oh, how nice, raised to the 5th power, and then y to the minus 1/3 raised to the 5th power all over x squared y. So clearly, let's work on simplifying that numerator. 2 to the 5th is 32. X to the 2/5 times 5 is x, I'm going to come over here, x to the 2/5 raised to the 5th power is equal to x to the 2/5 times 5 over 1. So that's x. The 5's cancel. 10 divided by 5, that's x squared. And this is y to the minus 5/3. Because minus 1/3 times 5 is minus 5/3. All of this is over x squared y. Now, let's look to simplify. If you notice, I have x squared in the numerator and x squared in the denominator, so they literally cancel out. So my end result is going to be 32 in the numerator, and I'm moving this entire term down below so that I have y times y. The price I pay is I change the sign to the 5/3. So this is equal to, just right underneath it, this is equal to 32. Now I'm going to write y to the first power is y to the 3 over 3 times y to the 5 over 3. So you add exponents. So that's y to the 3 plus 5 is 8/3. And that is our final answer. So there's some below this. Okay, so we're going to multiply. Again, we're going to be using our exponent rules, so you have to know them well. But really, we're not doing anything that much different than what we've ever done, except we're dealing with fractional exponents. So this is 5a. So that's z raised to the 2/3 times z raised to the 1/3 minus z to the 5th. So as in all cases, when I'm multiplying something like this, I just use the distributive law. I take this entire factor right here, z to the 2/3, and I multiply it first times z to the 1/3, and second times minus z to the 5th. So that's equal to z to the 2/3 times z to the 1/3. I'll put those in parentheses. I don't have to. And then I'm going to do minus z to the 2/3 times z to the 5th. And I'll put those factors in parentheses too. I hope you see all you have to do here is add the fractional exponents. And 2/3 plus 1/3 is 3/3. And 3/3 is just 1. So that first factor just turns out to be z to the first power, or just z. And my next one here, in order to add them, I have to make 5 with a common denominator of 3. And that's easy enough. That's 15/3. 15 divided by 3 is 5. So again, simplifying one more step, that's z minus z raised to 2 plus 15 is 17/3. And that's it. That is our final answer. That's the simplification they want to see. Now let's do again. Just a reminder, we're doing binomials, but they're not really binomials because I'm going to ask a question of you here. Why is x to the 1/3 minus 5 not a polynomial? Anyone have any idea? Think about it. X to the 1/3 minus 5 is not a polynomial. Why? Because 1/3 is not a natural number. Polynomials are restricted to having natural number powers. Remember our natural numbers, 1, 2, 3, etc. And that's not a polynomial. So this is very similar to multiplying 2 binomials. We're going to use the exact same method that we do before. So I don't need for you to see that over here. It was a fun question. I hope at least a few of you were able to intuitively think, well, what's wrong with it is it has x raised to the 1/3 power, and that indeed was what's wrong with it. Whether you articulated it or not is another story. That might be a good Canvas-based test question. So again, I take my first term, x to the 1/3, and I multiply it by the entirety of what's in parentheses, x to the 1/3 plus 2. Then I take my second term, which is minus 5, and I multiply it by all of the second factor. And now I just use distribution on both of these. So this is x to the 1/3 times x to the 1/3. So I add the exponents, and I get x to the 2/3. And x to the 1/3 times 2 is plus 2x to the 1/3. Now here again, just using distribution, minus 5 times x to the 1/3 is minus 5x to the 1/3, and minus 5 times 2 is minus 10. Then, like everything else, we collect like terms. And like terms are terms who have the same variables, and those variables are raised to the same exponents. So the answer is going to be x to the 2/3, and 2x to the 1/3 minus 5x to the 1/3 is 2 minus 5, which is minus 3, x to the 1/3 minus 10. And that is our answer for 4B. No, that's 4. Yeah. No, that's 5. Actually, 5B. No, it does kind of matter because some of you are only scanning through these And it's important that you see the right if you want to somehow correspond, because I'm absolutely fine that you fast forward these. So here we go. We're going to do a factorization. So this is going to require us to remember. No, that's what I want. How to factor. So here is my original sum. This is just a sum. 3x to the minus 1/2. And I'm literally not going to do anything with that minus 1/2. I really wish they would not have given you a minus 1/2. Because you're thinking, oh, wow, I have to make that into, well, just a really quick question. What would 3x to the minus 1/2 be if I were writing that, just this one term with positive exponents? Notice the base is x, not 3, but just x. So that's equal to 3 over x to the 1/2. But we're not going to worry about that, because oddly enough, what they want us to do is to factor out x to the 1/2 minus 1/2. So what do we do to find out what's in here? I take 3x to the minus 1/2 and I divide it by x to the minus 1/2. And these two terms cancel, and I'm getting a 3 there. And I have to do the same thing over here. So I have to come over here, and I have to, I've already written my minus sign down, so I'm just going to divide x to the 5/2 divided by x to the minus 1/2. Let me make my pin setting just a little bit smaller. Well, not that small. So that's equal to 7x to the 5/2. Now I'm going to bring x to the minus 1/2 across the division line up. So it's going to become x to the 1/2. So that becomes 7x 5/2 times x to the 1/2. So I add my exponents, and that's, which is 7x to the 3rd. So I literally write down 7x to the 3rd. Who would have thought it? It's kind of, how would you have done it? Well, that's what you have to do, is you go back and you remember the basic rules of factoring and you apply it in this case. Okay. So it looks like just a few more problems left. So we want to simplify radical expressions. We're going to assume all variables represent non-zero numbers, and we want to use rational exponents to simplify. So these are radical expressions, and I'm going to convert them to exponent expressions and simplify. So let's look at what number is this? This is 7a. So I'm looking for at the 8th root of x to the fourth. Well, that is by definition x. So my index becomes my denominator, and my power becomes my numerator. Well, that's equal to x to the 1/2. And they want you to, if I'm not mistaken, by looking at the book, simplify it back into a radical. So that's the square root of x. And if you want, you can write a 2 there, but you'll get lazy eventually and stop doing that. So let's do 7b. So we want to do the 6th root of 25. So the first thing we're going to do is rewrite 25 as 5 squared. So now remember, the index is my denominator, and the power under the radical is my numerator. So that's equal to 5, simplifying 2/6 to the 1/3. So that's the same thing is the cube root of 5. Now let's do the last one, C. We want to do the 4th root of r squared s to the 6th. So I need what's in the base to be raised to the same power. So 6 divided by 2 is 3. So I'm going to write r squared is r squared, but s to the 6th is s cubed squared. And now I'm going to use another exponent rule. Basically, we have if a times b raised to the r is equal to a to the r, b to the r, I have this, and I'm going to this. So this is the 4th root of r times s cubed squared. Okay, so now I can simplify. So now let's look at my base. That's r s cubed raised to a fractional power. My denominator is my index. My numerator is the power that the base is raised to. That's the reason I needed to have two things, a base raised to the same power. So this is r s cubed raised to the 1/2 power, which is the same thing as the square root of r s cubed. Yeah, 3 more problems. Not so bad. It looks really hellish, but it's not so bad. Practice will help. So we want to use rational exponents to write as a single radical. So we'll be able to do that. So what we're going to do is convert them to each one of these radicals. What we're going to do is we're going to convert it to a rational power, simplify, and then convert it back to a radical power. So this is number 8a. So the square root of x times the 4th root of x. Well, the square root of x is the same as x to the 1/2. And the 4th root of x is the same as x to the 1/4. So now I add the powers. 1/2 plus 1/4 is 2/4 plus 1/4. So that's equal to x to the 3/4, which is the 4th root of x cubed. So let's do another one. B, 8b. I have the square root of x over the cube root of x. So I'm going to convert the numerator into x to the 1/2 power and the denominator to x to the 1/3 power. Since 1/2 is greater than 1/3, I'm going to pull x to the 1/3 up, and it becomes x to the minus 1/3. I moved it across the denominator. So now the bases are the same. So this is equal to x to the 1/2 minus 1/3, which is equal to x to the 3 minus 2 over 6, because our common denominator is 6, which is equal to x to the 1/6. So that's equal to the 6th root of x. And our final one, literally, I haven't been reminding you all, but I hope you've developed good at-home study skills. Listen, people, we don't know if we're even going to, we might be having to, you might be taking classes like this in the fall. We just don't know. It just depends upon what happens when people start congregating again and whether COVID-19 sparks back up. We just simply don't know. Oh, well, the bases are not the same here. Let's go ahead and change that. This is 3 to the 1/3 times 2 to the 1/2. So what rule am I going to use? Well, notice there are rules where the bases aren't the same. It's the power of a product rule. That's a to the nth times b to the nth. So what I need to do is convert 1/3 and 1/2 to where I have a common denominator. So I'm going to convert 3 to 2/6. And this is going to be 2 times 3, 6, which is equal to 3 squared times 2 to the 3rd raised to 1/6. Did you see that? Tricky. Well, literally, these are just numbers. So 3 squared is 9, and 2 cubed is 8 to the 1/6 power. But 9 times 8 is 72, and 72 is raised to the 1/6 power. That was kind of tricky, right? So this is the same as the 6th root of 72. Finito. Okay, that's it.